that's what I thought. So number 5 is the integral of 5x minus 10 over 25x squared plus 4. And it's important, actually, that this is very similar to the problem right before this in terms of appearance. But the way you do the problem is a lot different from the problem right before this. So the problem right before this, the only difference is that the bottom here has a minus in it. So it's exactly the same as 5x minus 10 on top. But on the bottom, it's 25x squared minus 4. And that factors. And so the fact that that factors means that you should use partial fractions. This does not factor. And not only does it not factor, it's irreducible. And we know it's irreducible because it's the sum of two squares in the bottom. So when that happens, you try to make it match log and inverse tangent. And with a middle term, that's really challenging. But with it's challenging here too, but it's real hard with a middle term. Without a middle term, it's not as bad. And so what you actually do is you split it up. And so we split it up, and we're going to say, okay, 5 times x over the bottom, and then minus 10 times the integral of 1 over the bottom. And the reason we split it up this way is because if you let u equal the bottom, then du is 50x. And so this is a really good way to match the log form. It's in the form that we want because du being 50x, that x is sitting there. And then that does not work, but we can match inverse tangent. And so what we're going to do is on the one on the left, and I'm going to do this in 2 different colors for the rest of the problem. So we're going to say the one on the left, we're going to go with u equals 25x squared plus 4. So then du is 50x dx. So then the next step on this one is 5 times 1 over 50 integral 1 over 25x squared plus 4 times 50x dx. And we're doing that because we want on this green integral, we want it to be 1 over u du. And so we'll continue with that problem using that, but that one's very straightforward. The one on the right is not nearly as straightforward. That one's pretty tough. And so you want on the one on the right, you want it to match 1 over 1 plus u squared du, because if you let u equal the square root of this x squared part, so u then basically is just x, it's a constant times x, then du is just a constant, which is what's sitting on the top. And so to match this form, this 1 down on the bottom has to be a 1. And so we're going to factor this 4 out to make that happen. So we're going to keep the negative 10. We're going to factor a 4 out of the bottom. And so that's a 1/4 when you pull it out. But it's not like we're doing 4 and then 1/4 for u sub. It's like we're factoring a 4 out that's already in the problem. So when you factor that out, the 4 that's in the bottom becomes a 1, and 25x squared becomes 25/4 x squared, and then you have dx at the end. Does that make sense to everybody?
Yeah.
Okay, cool. All right, and so then on the first one, we've got it in the form we want. We've got 5 over 50, but that's 1/10. And then we've got the integral 1 over u du. On the second one, we've still got some work to do, but we need to pick a u. And since we already used u, we're going to pick the letter v. And v is like, because it's 1 plus u squared in the bottom, or in this case, it'll be 1 plus v squared in the bottom. V is whatever you square to get this. And so v is 5 over 2 and then x. So it's 5/2 x. And then dv is 5/2 dx. So then, okay, we've got 10/4, which is 5/2. I'm going to write it as 10/4 just in case you're looking at it later. it is random, more or less random, that 10/4 matches this 5 halves. That's not the reason it's 5 halves. So this is 10/4 right now. But now we need a 5 halves inside. And so we get 1/1 plus 25/4 x squared, and then 5 halves inside, which means we need 2/5 outside. Okay? And now the first integral is pretty much done. I'm going to leave it in the integral form until we do both of them at the same time, but you can go ahead and evaluate that if you want. The outside of that becomes 20/20, which is just 1, so it cancels completely. And then this is 1/1 plus v squared dv. And now, okay, that's 1/10 natural log absolute value of u minus inverse tangent of v plus c. And so we get 1/10 natural log absolute value of u, but u was 25x squared plus 4. And then minus inverse tangent of v, but v was 5x over 2, or 5 halves x, plus c. The only other thing we could do is we could drop the absolute value, but we've said a few times, I think WebAssign doesn't like that. Here you can drop it technically because 25x squared plus 4 is always positive, but you definitely don't have to drop that, and probably shouldn't with WebAssign. All right, does everybody follow that? You guys good? Okay.
Yeah.
All right, cool. All right, so then the next one we're going to do is number 13, and then I've got one in chat, and then we'll kind of add some more. And I'm glad somebody likes the Christmas colors. That was not on purpose, but I feel like we could all use that right now. So that's good. All right. Number 13 is right, Andrew? Is that the one we're talking about? All right, let's do number 13. And so 13 is 26 over 8, x minus 1, x squared plus 25. And then dx. All right, so this is the right one, right, Andrew? Just making sure. Yeah, okay, cool. So this one is partial fractions, and obviously it's on the worksheet with partial fractions, so I guess that would make sense. But if you're looking at this with a bunch of other stuff, it's partial fractions when you have a polynomial over a polynomial, and the degree of the bottom is bigger than the degree of the top, and the bottom factors. And that's the case here. The degree of the bottom is actually x to the third, because if you multiply that out, you'd get x to the third. So the degree is 3. The degree of the top is 0. This is already factored for you, which is ideal. And then you should double check that this doesn't factor further. So like if that was x squared minus 25, you should factor that more, but here you can't. And so this is factored the way you want it. And so we're going to start with partial fractions because it meets all those conditions. And so we come down here and we say, okay, we've got this fraction, and we're going to split it into a over x minus 1, because x minus 1 is linear. And so the idea is the degree of the bottom must be larger than the degree of the top. So the degree of the bottom, it's x to the first, so the degree of the bottom is 1. That means the degree of the top has to be actually smaller than that, which means degree 0, which is just a constant. So a constant a, we don't know what constant. We're going to try to figure that out. And then when you have x squared plus 25, that's degree 2 and does not factor down into degree 1. So then the degree of the top has to be smaller than that, but that means the degree of the top could be degree 1, or it could be degree 0. And so the way you indicate that is you put bx plus c, meaning, okay, you can have an x there, but you don't have to. If b ends up being 0, then okay, the thing was just a constant to begin with, but chances are b is not going to be 0. So like when we make one of these up at random, usually you get a non-zero thing for a, b, and c, but every now and then one of them zeroes out, and that usually makes the problem easier. But does this make sense to everybody? Everybody clear how to break that down?
Mm-hmm.
All right. Any questions? Okay. And so now we're going to multiply by the common denominator. And so we get x minus 1 times x squared plus 25 over 1. And we multiply both sides by that. So on the left, both factors in the denominator cancel, and we get just 26 on the left. On the right, this distributes to both fractions. So on the first one, the x minus 1s cancel, but the x squared plus 25 does not, and the a does not. So you get a times x squared plus 25, but then a 1 on the bottom. And then on the second one, x squared plus 25 cancels. So you get bx plus c times x minus 1. So any questions? So you please interrupt me if there's something that's unclear, because you guys have to do this on a test within 24 hours, maybe as early as 4 hours from now. I wouldn't recommend.
Why?
Go ahead.
Why wouldn't you just factor out 26 at first, and then
You could,
do
and then deal with the
over
1 down
both
here.
of those?
Sure, you could do that.
Okay.
So what that would do is, like, let's say I end up getting a is 52, then you're going to get a as 2, because 26 times 2 is 52. So it's just like you're going to have a 26 factored out of a, b, and c. Completely fine to do that, but not necessary to do that. Does that make sense? Okay. Other questions? All right. So then we're going to distribute the a now. So we get ax squared plus 25a. And now we're going to multiply out this binomial. So we get bx, or these binomials, bx times x is bx squared. So this is distributive property, or FOIL, or whatever you call this. It's technically called distributive property, but we get to there. And now we combine all the like terms, but like terms in terms of x. So x is the variable over here. So we're going to say, okay, all the x squareds go together. So we get a plus b x squared. All the x's to go together. So we get plus negative b plus c x. And all the constants go together, meaning the ones without x. So we get 25a minus c as the constant. You want to keep this easier on yourself, you want to force all these to be pluses. So if they're negatives, just make sure they're grouped correctly. But you do want pluses outside of here. And now that's typically an easier way to get it set up. All right, any other questions to here? Oh, my bad, I'm missing something in the chat. So oh, my bad. Okay, yeah, we can do one of those when you don't determine the numerical values of the coefficients. Yes, I think I know what you're talking about, Austin, and we'll do that here in a minute. All right, so this, the polynomial on the left has to be the same as the polynomial on the right. So like this polynomial on the left or on the right could be something like 3x squared plus 2x plus 1, or something like that in general. But it actually needs to be 26. So that means there can't be an x squared. So a plus b has to be 0. There also cannot be an x. So negative b plus c has to be 0. And then this is the only constant term. Well, that's got to be 26. Does that make sense to everybody? All right. So we're going to set up kind of a system of equations. So we're going to say, okay, a plus b is 0. Not kind of a system of equations. That's actually what this is. And then negative b plus c is 0. And then 25a minus c is 0. And now we've got to figure out how to solve for a, b, and c. And there's a lot of ways to do that. This one's kind of annoying because none of them have the same two variables.
Shouldn't 25a minus c equal 26?
Yes, not 0. Thank you. So please don't randomly change things. That should for sure be 26. The others should for sure be 0 because there's no constant there. But 25a minus c should be 26. That makes sense. Thanks. All right. So now, a lot of ways to go about this. I would recommend adding, what I would look at and immediately do is add those two. And so if I add those two equations, I get a plus c equals 0. Because if you add the ones on the left, the negative b's cancel, or the b and the negative b cancels. And then the zeros on the right get you 0. And now, if I use that equation with 25a minus c equals 26, then okay, that's 26a equals 26 if you add those, and you get a equals 1. Does that make sense? All right, so now we go back and we try to figure out b and c. So like we know a plus b is 0, so we know 1 plus b is 0, which means b is negative 1. And then negative b plus c is 0, so we know negative 1 plus c is 0. So then c is negative 1 if we work that out. So we get it there. Okay. Any questions? Okay, so we go back up. A is 1, B is negative 1, C is negative 1. So what that then does is it gets us that it's 1 over x minus 1 plus negative x minus 1 over x squared plus 25. And then you want to split this into, in this case, 3 integrals. And is everybody clear to there on how we're getting that?
Mhm.
Okay. Any questions? Okay, so because of time, I'm going to choose to skip these last 2 because that part is the same as the problem we just did. Does that make sense? I'm not trying to like ignore your all's questions, but like that's exactly this. Does that make sense to everybody? Just a little bit easier version, actually, but same idea. The first part will become log absolute value of x minus 1, and then log here and inverse tangent here. And I'll let you guys finish that up. But you do have the answers to this worksheet, so you can double check. But the work for those is just like the problem we just did, the first one. Okay? All right. Any questions on this problem? And then I'm going to kind of go down through the chat. As far as other questions is new.
I have a question, but
Sure.
it's a real quick question regarding partial fractions in general. So say
Yeah.
you have a polynomial on the bottom that factors out into 2.
Yeah.
Does it matter which one you put under the A and B?
It doesn't. But like if you're like, so if I do it the opposite of you, let's say you get A is 3 and B is 5, then I'm going to get A is 5 and B is 3. And so like whatever you get that corresponds to x minus 1, that needs to be the same as what I get that corresponds to x minus 1. So like maybe you have A with x minus 1 and maybe I have C with x minus 1, but I need a 1 there no matter what. Does that answer the question?
Yeah, I think so.
Okay, I tell you what, there's
'Cause
there's one in
I was looking at problem number 3.
number 3.
Because the bottom boils out to factors out to 3x plus 2 over 2x minus 3. And then when
Yeah,
I
okay.
solved it out, I got the negative 2 natural log before the positive 2 natural log in the answer. And I
As
wasn't
long
sure.
as it was with the right thing, that should be okay.
Okay.
Like, so if it's like negative 2 log of 3x minus 2, the coefficient of the one with 3x minus 2 needs to be the right. And then the coefficient of the one with 2x plus 3 or whatever you said, that needs to be right.
Okay.
Does that make sense?
Yeah.
Okay. Okay, so there's one in the chat, and I am going to go to the top, but there's one directly related to what we just did. Okay, there's a
Show the
couple.
last problem again really quick.
I'm sorry, what's that?
Could you just show the last
Yeah,
problem, like
sure.
the end or just the bottom? Okay, cool.
All good. Yeah, no problem. Okay, so somebody in chat, Lauren in chat is asking, I don't understand when to use partial fractions and when not to. And so let me show you this worksheet. And then if anybody still needs to see this work, I'm happy to pull it up again. But partial fractions should be used when you have rational expressions, meaning a polynomial over a polynomial. Does that make sense to everybody? Polynomials are things like these, where all of the powers of x are either 0 or positive integers. So it's like x to the 2, x to the 3, x to the 2, x to the 1, x to the 0. So it has to be these nice positive integer powers or x to the 0. So you have a polynomial over a polynomial. And then partial fractions only will work when the degree of the top is smaller than the degree of the bottom, or at least that's the only time it works directly. So like the degree on number 9 on the top is 2, the degree on the bottom is 3, and so we can use partial fractions based on that. And then the denominator must factor in order for this to work. So it's got to be rational expression, it's got to be the degree of the top smaller, and the bottom has to factor. Does that make sense to everybody?
Yeah.
Okay. If those happen, then we can use partial fractions to break it down. And if the degrees are the same, or if the degrees on the top, if the degree on the top is bigger, like on 10, 11, and 12, you start with long division and then you do partial fractions. Does that make sense? Yeah, let's do one of those in a second. And then somebody was asking, I believe, about this. Is that what Austin was saying in chat? I think it's Austin. Maybe it's somebody else, but somebody said that they don't understand the numeric, where you don't determine the numerical. I think it's this. Okay, let's do this. We will do one where you do long division, and I promise I'm going to get the stuff in the chat. It's related to this stuff we're talking about right now. So let's say you've got this. All right. Well, come on. There it goes. All right. So write the form of the partial fractions decomposition and don't solve for ABC. All right, so I'm going to put a ridiculous one up. So like, let's say I have x squared times x plus 3 times 2x minus 5 times x plus 6 to the third times x squared plus 25 times x squared plus 2x plus 8 and x squared minus 3x plus 10 squared. And we'll say there's a 7x plus 1 on the top of that. All right. So a couple things to check when you're doing these. One is make sure it's a rational expression, which this is. So it's polynomial over polynomial. Make sure the degree of the top is smaller than the degree of the bottom. The degree of the top here is 1. The degree of the bottom is huge. If you multiply that out, I don't know what it is. We can figure it out, but it's bigger than 1. And then make sure the bottom is factored, and make sure it's factored completely. So this one is, but you should think about it. So like x squared obviously doesn't factor. This doesn't factor, this doesn't factor, this one doesn't. Watch for these though. So x squared plus 25, that does not factor, but x squared minus 25 would. And then you can check these two, but they also do not factor. And so you need to make sure on these that it's factored completely. If it's not, you need to factor it more and like rearrange the factors so they're in a reasonable order. Does that make sense to everybody? Any questions? Okay, now the different things that can happen is you can have what's called linear factors. So that's when x is to the first. You can have a linear factor like this that is repeated. So it's linear because it's x to the first, but it's there 3 times. Does that make sense? Okay, you can have what's called an irreducible quadratic factor, which in the videos and the lectures, I talk a little more detail about that, but basically it's that it doesn't factor. It's more that if you were to factor it, you would need to allow for square roots of negative numbers, which we will not. But it's basically that it doesn't factor. It's an x squared, quadratic is x squared, and it doesn't factor. And then you can have a repeated irreducible quadratic. And those are the 4 cases that we'll see. And so the one that's the most misleading is when you have x squared, because x squared is quadratic, but it's not irreducible. So irreducible means it has no zeros. There are no x-intercepts if you were to graph it. Well, x squared for sure has an x-intercept. It's 0. And so the way you treat this is as though it's and it happens to be quadratic, but it's also a repeated linear because it's x to the first, but it's there twice. And so we treat it as a repeated linear. You can think of it as quadratic, but it is not irreducible quadratic. And so quadratics we would factor completely, and so x squared we treat as x times x. Now, the way you handle this for the form of the partial fractions decomposition is when you have a repeated linear, every power of that factor gets its own fraction. So if it's to the third, every power from 3 down gets its own. So you get the first power, the second power, and the third power. If it's to the 5, if it's to the 5th power, you get whatever it is to the first, to the second, to the third, to the 4th, and to the 5th. Does that make sense? Okay, when it's x squared, it's only there twice, but that means you get it to the first and to the second. So we're going to say, okay, it's a over x plus b over x squared. And every time that it's linear or repeated linear, the numerator is a degree 0 polynomial, which is a constant. And so you just put a single letter on the top. Now, when it's a linear that's distinct, like these, meaning that x plus 3 is only there once and 2x minus 5 is only there once, then, okay, you do c over x plus 3. Yeah. Charlotte, that's a really good question, and give me a second, and I'm going to explain why at the end. Okay? Good thing to know it's not, but let me talk about it right at the end. All right. And then repeated linear, you get e over x minus, or x plus 6, f over x plus 6 squared, and then g over x plus 6 to the third. Does that make sense to everybody? Yeah, so Hazem's saying something mostly right. You would only use that if it's irreducible. The rationale why is not as clear from what we've said, but I will explain that quickly at the end, okay? All right, everybody good to hear? Okay, and so then these irreducible quadratics, this is when you get like hx plus I over x squared plus 25. And then jx plus k over x squared plus 2x plus 8. And so because it's an irreducible quadratic and the bottom's degree 2, and then that means the top could be degree 1 or degree 0, so you allow for degree 1. If it happens to be degree 0, then okay, you get 0 for h or 0 for j maybe, and that'd be okay. And then x squared minus 3x plus 10, that's irreducible. And it's repeated, so you do it the same way as a repeated linear. Every power gets its own, but the top is first degree potentially. So lx plus m over x squared minus 3x plus 10, and nx plus, we're going to skip o so it doesn't look like a 0, p over x squared minus 3x plus 10, and you can pick whatever letters you want. Don't use x. But you don't have to worry about like getting them in alphabetical order or anything like that. Whatever works. But does that make sense? All right, there's one question in chat about why would it not be bx plus c? That's a really good question. I do want to talk about that, but any other questions about how I did that problem? And the person that asked about that in chat, did that answer the question? I see what you're saying. Okay. Okay, yeah, but you're also, the one you put in chat where it's x squared over x squared is a long division one, and so we will do one of those next. That was what people were asking to do on that worksheet anyway. Okay, all right. In chat, Charlotte, why is this not bx plus c? Because of this. If you put bx plus c over x squared, you can rewrite it this way. And bx over x squared is b over x. So this is already taken care of by that one. Does that make sense? Like you're trying to get all of the component fractions. And so you're already taking care of that possibility. Yeah, no problem. And it's weirder algebra to show that that's the case here, but you can manipulate things to show that like if I put fx plus g, I can mess with that so that I could split it off into here and only have to deal with the constant here. And then same, if I put like gx squared plus hx plus I here, I could mess with it enough where I can split everything off and get these separated and only have to deal with the constant. It's easier to see when it's x squared, but that's a really good question. That's why you do it the way you do it. That's why you do not up the powers when you go to these higher powers of the repeated linear, okay? All right, other questions so far? Okay. Okay, so then somebody was asking, and somebody in chat's asking about what do you do when it's same degree or if the top's bigger. So I'm gonna do problem 11 on the worksheet. This is worksheet 2 on partial fractions. And then after this, we're gonna move off of partial fractions. Well, we'll talk about the very first question in the chat and then move off of partial fractions. So we can get to some other stuff. So when the degrees are the same, or if the degree of the top is bigger, you actually start with long division. So you do 2x squared minus x into 8x squared plus x minus 3. And so the way you handle that is you divide the first term here divided by the first term here. Well, 8x squared divided by 2x squared is 4. And so you put that on the top and you actually line it up with the other constant. So if it was like 4x, you'd put it here. If it's 4, you just put it over the 3. And now you multiply. You do 4 times 2x squared is 8x squared. And 4 times negative x is negative 4x, and now you subtract. And now that's 0 on the first one, and that's 4x on the second one. And you bring down the 3. It's this minus goes to everything there. So it's minus negative 4x. However you want to denote, that's fine. I make a huge negative sign, meaning it's going to go to both of those. Except it's 5x, my bad. X plus 4x is 5x. And so then what that lets you do is it lets you rewrite it as 4 plus 5x minus 3 over 2x squared minus x. So that's what the division means. It's the quotient plus the remainder over the original divisor, over this. Now, this could be anything from there, but in a lot of cases, it's partial fractions. Or maybe it's irreducible, or maybe it's just a simple one at that stage. But now you do partial fractions on this because the bottom factors to 2x minus 1 times x. So you'll do like a over x and b over 2x minus 1. Does that make sense without me finishing that problem? Does everybody follow that? Okay, but what the long division process does is it gets you a polynomial. So this could have an x or an x squared in it. Get you a polynomial that's separate from the fraction, and then it gets you a fraction where the degree of the top is smaller than the degree of the bottom, because that's when you stop long division, when this degree is smaller than this degree, okay? All right, and so this is one that generally will be partial fractions, but if you want to practice more of those, there are several on that second partial fraction sheet. And I know you don't have worked out solutions, but you do have the answers. And so you start with this, and then you can work it from there and then get the answers back. All right. Man, I'm going to try to get to everything in chat. The very first question in chat was this, and I want to start it, but not finish it. But it is on the second worksheet. I don't know if you knew it was on the second worksheet, but it's on the second worksheet, and it's number 15. And there's a hint on it. And this is a tricky problem because the hint's not obvious. It says to let u equal the square root of x minus 1. And so what you do is if u is square root of x minus 1, then du is 1/2 times x minus 1 to the negative 1/2 times 1, because of the chain rule, dx. But that's 1/2 square root of x minus 1 dx. So it's real weird because you want to get du at the end of the problem. Well, there it is. So you move this over and you put a 2 here, which is really 1/2, and a 2 outside. And then it's weird because u's not here at all, but I can solve this for x. So u squared is equal to x minus 1 because of this. So x is u squared plus 1. I guess we will finish this one. And so we get it to there. Does that make sense? Now that could easily be a problem where this is now partial fractions because this could factor, but this one doesn't factor and it's already inverse tangent. So this one's a little quicker. But if that factored, you would use partial fractions. Here it's just that, and you get 2 inverse tangent of the square root of x minus 1 plus c. And so it's a real tricky problem. I should probably change that worksheet so it ends up being partial fractions. If this was x plus 1, it would probably end up being partial fractions, right? Does that make sense? Man, that's a weird problem. All right, we're good? Okay. All right, so I'm going to go back up to the chat and try to fairly answer as much of this as I can. Okay, Jordan asked for number 7 on partial fractions 1 and number 3. Jordan, it's not that I don't want to answer those questions, but because we've been doing partial fractions the whole time, I'm going to wait on those, and then I will try to my best to get to them at the end. Alex, we've got one that should involve trig sub, and so we're going to do this one. Man, I feel bad that I'm skipping that question, but give me a minute, and hopefully we'll get to that too. Okay, so when we're doing this, you should mess with this for a little while and think about, or not mess with it for a little while, but think about u sub for a little bit, and it doesn't work real well. And so then trig sub is the next best option on this because it'll get rid of the square root. So we're going to choose for x to equal 6 secant theta. And just kind of as a review, if it's going to be in this form, so if it's going to end up being 1 minus a trig function squared, you want to use sine. If it's going to end up being a trig function squared minus 1, you want to use secant. And then if it's going to be addition in either order, you want to use tangent. So subtraction, the order does matter, which means wherever the x is, that's where the trig function is going to be. So here I knew it was going to be secant squared minus 1. So I want that. If it's 1 minus a trig function squared, we want this one. And then addition, the order does not matter. And I can do it in either order. Okay, I'm sorry. Back up here. Laura asked, why did I solve for x? And it's because I needed to get that in terms of u. Does that make sense? Sorry, I was ignoring the chat. Not on purpose, I just did. Okay, all right, cool. Yeah, no problem. Okay, I'm not sure what should be 5x minus 3. I hope I was right, but if I made a small mistake and Andrew's right about 5x minus 3 somewhere, hopefully you saw that in chat. Sorry, I don't know what that was. I was scrolled up in the chat when you said that. All right, so now we got 6 because we want to match the 36. We got secant because we want secant squared minus 1. That makes dx, whoops, that makes dx 6 secant theta tangent theta d theta because it's the derivative of this. So we're going to go over to the side and now do the square root. So we get 36 secant squared theta minus 36. And now we factor the 36 out. secant squared minus 1 is tangent squared. And we get 6 tangent theta. Does that make sense? All right, so then we got the square root gets replaced with 6 tangent theta. The x gets replaced with 6 cubed secant to the third theta, because it's x cubed. And then the dx gets replaced with 6 secant theta tangent theta d theta. Oops. All right, so we're going to pull out all the coefficients. So we pull out a 6. We pull out 1 over 6 to the third, and we pull out another 6. And then we're going to simplify this down and get tangent squared over secant squared. And now we're going to figure out where to go from there. Questions to that point, and I am looking at the chat, so if you have a question and you want to put it in there, you can. Okay. So now you're going to try to mess with this to get it. So that everything we've done is kind of the same on all the trig subproblems so far. This is where it's different from one problem to the next. And you have to mess with this and see what you can figure out. There's probably a couple good ways to go about this. One thing we can do outside is just go ahead and cancel the 2 6s on top with one of the, or with 2 of the ones on bottom, so you get 1 6. And then I'm going to rewrite this as sine squared over cosine squared because of the tangent. But then over secant squared is the same thing as times cosine squared over 1 because you flip the bottom and multiply. Okay, and then I've got a question in the chat I'm going to answer next. But do we understand what I did here? Okay, so the question in the chat is, how did I determine that x is 6 secant theta? So whenever you're trying to do trig sub, you pick a coefficient and you pick a trig function. You pick the coefficient to make the coefficients in the square root, which, or whatever we're using the trig sub on, which to make the coefficients match. So there's nothing to cancel here. So you don't put anything in the bottom, but you need to end up with 36. So you put a 6 there. And then because I want to end up with a positive trig function squared, I know that secant squared minus 1 is tangent squared. And I knew I was going to end up with a trig function there minus 1. So I wanted secant there. Does that make sense? Okay. And then where did the 1 over 6 cubed come from? That came from here because when I plug in for the x to the third, yeah, no problem. And when I plug in for x to the third, you plug in what x was to begin with. So that was 6 to the third, secant to the third. And then I pulled out the 6 from the top. I pulled out the 6 to the third from the bottom. And I pulled out the 6 from the end and got it to there. Does that make sense? Okay. All right. Now that I've got it to here, this is a good idea because the cosine squareds cancel. And we get it to there. And now sine squared is an integral that's not a basic form, but we have a definite strategy for how to do. When you have even powers of sine and cosine, you use the half angle formulas to rewrite the integral. And the half angle formula for sine is sine squared theta equals 1/2 times 1 minus cosine of 2 theta. And so we get it to there. Question? Okay. So now we split that into two integrals. We've got 1/12 on that now. And the 1/12 goes to both integrals. Yeah, Andy, I'll do that next. Somebody in chat's asking for the half angle formula for cosine. We don't need it on this problem, but you definitely need it for a lot of problems. And so it's that, okay? And it is right that they're both cosine. The difference is minus for the sine squared and plus for cosine squared. Okay, so we get it to here. We do the integral of each one. The integral of 1 d theta is theta. The integral cosine 2 theta d theta is 1/2 sine 2 theta. And now we're going to try to go back to x. All right, any questions so far? Yes, Charlotte, thank you. I was going to ask if whoever sent that earlier could do that. So Charlotte in the chat, if you guys look in the chat, she sent a PDF of a bunch of trig stuff that would be very helpful. You can't have an electronic copy during the exam, but you can print it out and use that. Or write it down if you don't have a printer and write stuff down. All right. So at this point, we try to go back to x. So you go to the original trig substitution. Actually, we'll do this in green, so let's keep it separate. So x is 6 secant theta, and so then secant theta is x over 6. So you solve for the trig function. And now, so the question about respondus actually depends on the instructor. Most of us are not using it for this exam, but if it's clear that everybody math weighed all the answers, that will change. Does that make sense? All right, I think Tony is doing something on Zoom, if you have Tony. And yes, Santi, the 1/2 came from the chain rule. U sub, technically, it's the reverse of the chain rule. So like U is 2 theta, du is 2 d theta, so 2 inside and 1/2 outside. Does that make sense? Okay, yeah, no problem. Yeah, U sub is the chain rule, just in reverse. Okay, and so now we draw the angle theta in quadrant 1. And so secant is r over x, or hypotenuse over adjacent, however you like to think of trig. And so you get that, and then the opposite side, you figure out using the Pythagorean theorem, and you take the hypotenuse squared minus the other leg squared and take the square root. So you get square root of x squared minus 36, which should match the square root we started with. And now we're trying to use this to go back to x. Well, this is good when you have like sine of theta or cosine of theta or secant of theta, but not if you have sine of 2 theta. So you use the double angle formula. And I'll go ahead and write those up, but I'm sure they're on Charlotte's sheet, which would be awesome. So sine of 2 theta is 2 sine theta cosine theta. And that one actually comes up probably a lot more often than cosine 2 theta, because both of these are cosine 2 theta, and then when you take the integral, they're both going to become sine 2 theta. But if you did see cosine 2 theta come up, there are a few different forms of that identity, but it's this. Those are called the double angle formulas. So we're going to replace sine 2 theta with 2 sine theta cosine theta, so that we can get everything off of the triangle. And now, when you have theta completely by itself, not in a trig function, you want to use inverse trig in order to simplify that. So theta is the inverse secant, in this case, of x over 6. And then on this last step, the 2's cancel. So you get 1 over 12. And then sine theta, you read off of the triangle, that's y over r, or opposite over hypotenuse. So it's the square root of x squared minus 36 over x. And then cosine is adjacent over hypotenuse, or x over r. So it's 6 over x. And then you can simplify this, but not a whole lot. So the 12 cancels with the 6, and you get a 2. That's a 1 on top. And so you get 1/12 inverse secant of x over 6 minus the square root of x squared minus 36 over 2x squared plus c, and then that's the answer. All right, lots of stuff going on in that problem. So if there are any questions, please don't worry about asking. So you're welcome to send them in the chat about any of this. And you're welcome to unmute yourself and ask. Just let me know if you have any questions. You guys getting it? Okay, let me go through the chat and see what else we've got in here. Oh, my bad. New message. If you're doing bounds. Okay, so that's a good question. So Ben in the chat is asking, if you're doing trig sub with bounds on the integral, do you need to modify the bounds at all, or do they stay the same? Well, you do need to modify, but the problem is it's a little weird. So like, if I was doing this problem, I think it was that, right? Yeah. Let's say from 1 to 3. Oh man, we can't do that. Let's do from 6 to 10. So if I was doing that, the thing that happens is if you're going to keep okay, 2 answers to the question, 2 separate answers to the question. What I would recommend that you do is I would recommend that if you have this, you go through and do this whole problem without the bounds. And you don't say, okay, this is equal to this. You just say, okay, I'm going over to the side and I'm doing all this work to get my antiderivative. And then I would say, okay, that's then equal to this answer. From 6 to 10, and now plug in the x's, plug in this, or plug in the 10, plug in the 6, and subtract, where the work for this step is everything that we just did. And so that is how I would recommend doing it, so you don't have to mess with the bounds. If you choose to keep the bounds, then when you change to d theta, you have to figure out what theta corresponds to x equals 6 and what theta corresponds to x equals 10. And probably the easiest way to write that would be, it'd be like 6 would become inverse secant of 6 over 6, and 10 would become inverse secant of 10 over 6. And then at this stage, you could plug that in, and then you'd have to draw the triangle anyway. That's not how I would recommend doing it, but that's what you would do if you're going to keep the bounds. Does that answer the question, Ben?
Yeah, thank you.
Okay, yeah, no problem. All right, other questions so far? All right. So now I'm going to go back up this chat and see. We had this question. Okay, so some of the questions in here are more partial fractions, which I'm happy to do. I'm just going to do them at the end if there's nothing else. So yeah, like the one that Emily put in, 10x minus 7 over that polynomial, that is also partial fractions. Charlotte, the one you put in there, I love that problem, Charlotte, but it is a weird, weird problem. Where'd you find that problem? Just curious. Is that on your homework somewhere? Oh, you're texting. It was a WebAssign. Okay. Then
Yeah, it was on WebAssign. I don't
That's
know.
okay. It was not on my website. That's fair. All right. I don't think. Did I put this on my website? It's
I
not
had-
that.
I
Go
had
ahead.
like Iwona, and it was on
And
hers.
she put it on there.
Yeah, it took me like 20 minutes.
All right. I would not have made you do this, but all right. That's fair enough. Let's do it. Ivana did. All right. Fair enough. So there's a couple ways to go about it, but I think the best way to do is to factor that. So I would make this 3 log of x minus 3. Oh man, does that not factor? No, it doesn't. All right, my bad. I thought it was going to factor. So then, okay, it's not as bad as I thought. I don't think. We'll find out. I haven't done the problem. So when you see that problem, my first thought was let's factor that. And if it was -6, it would have factored. Make sure it's not -6, but if it had factored, you could split it like multiplication inside of a log. You could split into addition. Does that make sense? Okay. So then when you see a problem like this and there's not a good way to start it, sometimes the options, okay, so we're going to find out how hard this is because I've not worked it. It is addition, not subtraction. So then, okay, the only thing to think to start is to let u equal the whole thing. Like the 3 doesn't matter. You can factor that out. But let u equal the whole thing and try to let dv equal dx. So we'll see if I can do Ivana's homework. I think I can. All right. Yeah, we can get to that too, I think. And so we get that set up. Does that make sense? And I'm hoping this is going to work. We're going to find out. So now we're going to take the 3 out and do uv. So that's x times x squared. Man, I'm sorry. U is log of that. What am I doing? So du then is 2x minus 1 over x squared minus x plus 6. Oh, this is awful. All right. All right, so we got uv. So we got x log of x squared minus x plus 6 minus v du, but v du is 2x squared minus x over x squared minus x plus 6 dx. And I'm going to just carry the 3's to both of those. Okay, does everybody follow where I'm getting that? This is now a problem where the degree of the top is equal to the degree of the bottom, so we should do long division. So we're going to go over to the side and do x squared minus x plus 6 into 2x squared minus x. And then we'll put a plus 0 there so we have a spot for everything. And that's 2. So then you get 2x squared minus 2x plus 12. That's then 0. That's x, and this is minus 12. So we get 3x log x squared minus x plus 6 minus 3 times the integral 2 plus x minus 12 over x squared minus x plus 6 dx. Now we split that into 2 integrals. All right. Okay, questions to there? Now, this, it would be ideal if that was factorable, but it's not. And it's an irreducible quadratic. So irreducible quadratic, you know that it's that because b squared minus 4ac, the thing you get from the quadratic formula, that's negative. So here that's negative 1 squared minus 4 times 1 times 6, which is negative 23. And so this is going to be a horrendous problem where you have to do log and inverse tangent and complete the square. And I am going to not do that because of time, and because given that the test is tomorrow, if you're good with everything else, I would worry about this. And now that I say it, Ivana will put one on her test. I don't think she will, though, but I don't know. I did do one in the video from yesterday's lecture where you have to do completing the square, and you would do that on here. And so if you want to watch my lecture from yesterday, that's on the YouTube channel, and it's under, lecture videos after exam 1, before exam 2. That's yesterday's lecture, and I go through one like this. But like this part, we're done. This part's 6x, and then this part is another 15-minute problem. Okay, how did I get du? Du is 1. So the intermediate step is that it's 1 over x squared minus x plus 6, but then times 2x minus 1 because of the chain rule. Does that make sense? Okay, I just went ahead and put it on top. Sorry. That's a rough problem. But do you guys follow that? Man. All right. Okay. Now back up. I'm trying to go through the chat mostly in order. If I'm completely skipping, I'm really sorry. I'm not trying to. I'm trying to skip for now more partial fractions, but if that's all there is, we'll go back to that. Okay, yeah, so Taylor's saying it was in the bonus. I mean, it's a really good problem, and it's one I would put as a bonus question on a test, but I would not put it as a standard question on the test. And if you're in my class, I wrote your whole test. If you're in Adam's class, I actually wrote your whole test too. If you're in Ivana, Tony, or Fang Cheese, I wrote half your test, and then they wrote a written part for half your test. Not like way harder, it's just written. They want to grade your work and stuff, and I wrote some different types of questions with WebAssign to do the same thing. All right. So yeah, I doubt you'll see you there. I think I've gotten to everything in chat that wasn't partial fractions. Is there anything in chat that I'm missing? I'm not purposely missing it, that is not partial fractions, and then I will go back and do the other partial fractions questions, if that's the case. Does anyone have any questions on stuff that's not partial fractions, just because I feel like we've spent a ton of time on that? Okay. Yes, okay, sorry, Nick, and I think I missed that, and you said that before, or somebody had. Yeah, powers of sine and cosine, my fault. I think I saw it and was not trying to ignore it, just forgot about it. Okay, so if you have powers of sine and cosine,
Can you do one where they're both even? I mean,
they're both even. Sure.
Yeah.
So how about we do both? Is that okay?
Yeah.
Okay. So when you're doing the secant and tangent is a similar thought process, but there's not a quick rule for secant and tangent. For cosine and sine, there is. If one of the powers is odd, you should let u equal the other one. And so like this one, the power's odd, so you let u equal sine x. And this is the easiest way to do it, but it's also probably the only effective way to do it in most cases. So you do not want to use half angle formulas unless it starts as all even. So these are not both even at this stage, so you at no point should be using half angle on this. We should use this approach. So what you do is you split off du. And yeah, Lauren, next I will do a secant and tangent. And we'll make it so they're both even. But you split off du like that, and it leaves, because there were 5 there before, there's now 4 because you took one of them over here. And now you're trying to get everything in terms of u. So this is already in terms of u, but this one's not. And so we can rewrite that as 1 minus sine squared. Does that make sense? All right, so we've got u to the 4th times 1 minus u squared squared times du. And now you expand that. So if I expand that, I get 1 minus 2u squared plus u to the fourth du. And now the u to the fourth distributes. So I get u to the fourth minus 2u to the sixth plus u to the eighth du. And I'm going kind of fast, sorry. Questions? I'm not trying to speed through it. Everybody good to hear? Don't hesitate to ask questions. Like, I know this is weird. All right, you guys good? Okay, so then this is now a polynomial, so it's 1/5 u to the fifth minus 2/7 u to the seventh plus 1/9 u to the ninth plus c, and then u is sine x. So that's 1/5 sine to the fifth minus 2/7 sine to the seventh plus 1/9 sine to the ninth plus c, and that's the answer. All right. We good? Okay, so for sine and cosine, that works when one of them's odd. When they're not odd, when they're both even, then you use half angle formulas. And these are the ones I wrote earlier, but sine squared is 1/2 times 1 minus cosine of 2x. And cosine squared is 1/2 times 1 plus cosine of 2x. And so you have to be careful with these identities because you only should be using them when the powers start as both even. So like over here, if you start using half angle, it's going to make this problem like very, very difficult or probably impossible to mess with from there. So you only want it. I'm sure there are real weird cases where this isn't true, but in almost every case, the only time you should be using these on an integral is if you start with even powers of sine and cosine. If one of them's odd, you should automatically use this approach. If they're both even, then use half angle. And so what we do is we replace each of them with that. And so we get 1/2 times 1 minus cosine of 2x times 1/2 times 1 plus cosine of 2x. And now we're going to factor the two 1/2s out, so we get 1/4. And now we're going to distribute this through. So if you distribute that, you get 1 minus cosine squared of 2x because the middle terms cancel on this one. So you get like plus cosine 2x minus cosine 2x, and those cancel out. And so now you split this into two integrals. And now we've got more to do, but do we follow it to here? Everybody good? Okay, so then the first integral should probably be easy. The second integral is again powers of sine and cosine where they're both even. So we're going to use half angle again. So we get 1/4 x minus 1/4 times 1/2 integral. This time it's 1 plus cosine of 4x. Because the way the identity works is like whatever's here, then, okay, over here it's double whatever was in there to begin with. So if it's 2x here, it's 4x over here. If it's 7x here, it's 14x over here, and so on. And so now we're going to split this into two integrals.
Usage, huh?
Question?
That's
Good.
a new session for a while.
All right. And so we get that.
Read one? No. I'm gonna wake up and take my exam in the morning.
All right. And so we get it to this.
I'll come in and cuddle with you here in a bit. No.
And then that's the answer. Does that make sense? Questions on that?
Should the 1/8 be negative in the final answer?
May be negative. No, but it's because, Andrew, I subtracted those. So I made this 2/8 minus 1/8 and just combined them. You see what I'm saying? You're good.
Yeah, my bad.
Completely fine. Everybody good on that? Okay. Other questions? Okay. So now, the next question that wasn't partial fractions, and I'm happy to go back to partial fractions here for the last part of it, but the next question was, could we do one where it's powers of secant tangent and they're both even? So that's something like this. For these, you should think through two possibilities for the easiest setup. So we're either going to let u equal secant or u equal tangent. And hopefully one of those works. Sometimes they both work. Sometimes only one of them works. Sometimes neither of them work. And then if neither of them works, it's different from problem to problem. You do not do the same thing every time. But the idea is, if we're going to use this, then du is secant tangent. If we're going to use this instead, then du is secant squared. And you have to separate out du. And then after you separate out du, the one that is not u needs to then have an even power, because we're going to rewrite that one. So like, if I separate out secant tangent, I'm going to be left with 3 secants and 3 tangents. Because u is secant, we don't care what power is on secant at that stage, but we do care what power is on tangent, because we've got to rewrite that one. So tangent being to the third means that this is not a good approach, because if you rewrite it, you're going to get a fractional power. Does that make sense? Okay, and so then the other approach, if we do that, go with green, so u is tangent, du is secant squared. If we separate out secant squared, we're going to have 2 secants and 4 tangents. Well, we don't care what tangent is this time, because u is tangent. So this could be 4 or 5 or 7. We don't care. But we do care that secant is now even, because we need to rewrite it. Well, the fact that that's 2, that's good, because then we can rewrite it easily in terms of tangent. So we're going to go with this setup. So we're going to go u equals tangent, and du is secant squared. But the stuff I'm writing in red over there, that's kind of the thought process. You think of those 2 possibilities, and hopefully one of them works. If they don't work, then you try to be creative, because it's not the same every time. You mess with it and mess with identities and see what you can do, kind of like one we did earlier, or in the review session earlier today, we did one where I messed with it and did it a wrong way, and then went back and we fixed it and did it the right way. But you have to mess with it, and you have to be willing to try a couple different things. But if one of these 2 approaches works, it's very systematic. My bad, this should be an X right there. But we're going to separate out the du. That leaves 2 secants there and 2 secants next to the dx. So this part is the du. And now secant squared is the same thing as 1 plus tangent squared, which is one of the trig identities that we, man, I guess you don't have to memorize, but you should have them on a formula sheet somewhere. And so now that's the du. So now we get the integral 1 plus u squared times u to the fourth times du. And now you distribute. And now it's 1/5 u to the fifth plus 1/7 u to the seventh plus c, and u is tangent. So we get 1/5 tangent to the fifth plus 1/7 tangent to the seventh plus c, and that's the answer. All right. Questions on that? Okay. All right, so I've got a few questions in the chat. There's a couple about trig sub, and then there's a couple about partial fractions. I'm going to try to do one of each of them before the time is up. So let me start with trig sub, and then we'll do a, did we do a trig sub just now? No, we did one. Okay, let me start with partial fractions, then we'll do trig sub if we have time. Okay, so the partial fractions that people were asking, man, there's a ton of them. Actually, I don't know. Somebody have a partial fractions they want me to do? Number 7 on partial fraction worksheet 1, and number 3. Let me look at those and see. So the first partial fractions worksheet. Let's do number 3. I think that one's probably a couple of years we're done a while ago. Okay, cool. Okay, let's try number 3 on that first worksheet on partial fractions. So we've got the integral of 25 over 4x squared plus 23x minus 6. Okay, so some of the questions we were talking about before is how do you know this is partial fractions? Well, it's a polynomial over a polynomial. The degree of the top is 0, the degree of the bottom is 2. So the degree of the top is smaller than the degree of the bottom. And the bottom factor. So we need to go factor the bottom. And there are a couple ways to go about it. Probably the most straightforward way, or I think the most straightforward way, is you take AC. So like A is 4, B is 23, C is -6. And so you need to come up with 2 numbers that multiply to AC. So multiply to -24 and add to B, which is 23. And so that's positive 24 and -1. You use those to split the middle term. And now you factor by grouping. So you get x plus 6, 4x minus 1. Or however you learn to factor is fine, but you should get it to x plus 6 times 4x minus 1. And now you come to the side somewhere and do the decomposition. So you get 25 over x plus 6, 4x minus 1. That's then a over x plus 6 plus b over 4x minus 1. And then we multiply by the common denominator, which is x plus 6, 4x minus 1 over 1. And so we get it to their questions to there. All right. So then you distribute the A and distribute the B and combine like terms. And so the left-hand side is 25. That means the right-hand side has to be 25, which means 4a plus b is 0 because there's no x. And then negative a plus 6b has to be 25. And now probably what I would do is multiply that bottom one by 4. And write the top one above it, and then add them, and the A's will cancel out. So I get B equals 4, and then 4A plus B. So 4A plus 4 is 0, so then A is -1, because you subtract 4 and divide by 4. That makes this now the integral of -1 over x plus 6 plus 4 over 4x minus 1. We split that into 2 integrals. And now the first one is negative log absolute value x plus 6. The second one's a quick u sub, but it's 1/4 log absolute value 4x minus 1. Those 4's can cancel. But just because of time, I'm not going to write that very last step. But you can cancel those 4, the 4 and the 1/4 out. But that answer will work. Does that make sense? Okay. And then let me see what 9 and 10 on the trig sub worksheet were. So yeah, so let me pull both of those up. There's a couple ways to go about them. But any questions on that partial fraction before we go to that? All right. So 9 and 10 on the trig sub worksheet, I think you can get around trig sub on both of them if you want. But 9 is x cubed square root 25 minus 7x squared. And I'm sure I meant for you to do trig sub on that one, but I think you could get around it with u sub. On 10, you should for sure use u sub. So 10 you would let, I'm not going to do all of 10, but you would let u equal 4x minus 11 and du equals 8x dx. Does that make sense to everybody? I'm going to take that as a yes. So you get like u to the -1/2 du once you mess with that on that last one. On 9, I assume when I work out solutions, I use trig sub, but you could mess with it and use u sub. Let's do it with trig sub because I think that's what I wanted you guys to do. But when you do it, you're going to pick x to be 5 over the square root of 7 sine theta. And so it's sine theta because it's going to be 1 minus a trig function squared. So you should pick sine. And then it's 5 over radical 7 because you're going to get rid of the 7 and you want to end up with 25. Does that make sense? Okay. And so then du is then 5 over radical 7 cosine theta d theta. And now we're going to do the square root stuff on the side. So we get 25 minus 7 times 25 over 7, because that's what you get when you square that, sine squared theta. The 7's cancel, so you get 25 minus 25 sine squared theta. The 25 factors out. 1 minus sine squared is cosine squared. And then the square root of that's 5 cosine theta. So, okay, so we get 5 to the third, so 125 over the square root of 7 to the third, which we'll leave for now. And then sine to the third. And then instead of the square root, we get 5 cosine theta. And instead of dx, we get 5 over square root of 7 cosine theta d theta. Does that make sense to everybody? right, so then we're going to pull out 5 cubed over the square root of 7 cubed. We're going to pull out 5, and we're going to pull out 5 over the square root of 7. And then condense this and get sine to the third theta cosine squared theta d theta. We good to there? Okay, so on the outside, that gets us 5 to the 5th on top, square root of 7 to the 4th on bottom. And then this is a u sub, it's powers of sine and cosine. One of them is odd, so we're going to let u equal the other one. Du is cosine, so du is negative sine. So we split that up. We put a negative there, so then we multiply the outside by a -1 as well. And that gets us -5 to the 5th over 49, because square root of 7 to the 4th is 7 squared, which is 49. And then we want to rewrite this in terms of u, so we rewrite this one as 1 minus cosine squared theta times cosine squared theta times negative sine theta d theta. So we get 1 minus u squared times du. And then that's u squared minus u to the 4th inside. And then we get -5 to the 5th over 49 times 1/3 u to the 3rd minus -5 to the 5th over 49 times 1/5 u to the 5th plus c. That's -5 to the 5th over 147, and then u was cosine, so cosine to the 3rd theta plus 5 to the 4th, because one of the 5 cancels, over 49 cosine to the 5th theta plus c. And now we got to go back to x. It's a fun problem. You guys follow it? Man, they're not all this bad, but this one is. All right. So then you go to the original substitution and draw a triangle. So based on that very top left part, x is 5 over the square root of 7 sine theta. So sine theta is x square root of 7 over 5, which means we label the triangle like this. And when we solve it, we get square root of 25 minus 7x squared, which is good because it matches the square root in the beginning. And now you get cosine off of both of those. So you get, or for both of these, so you get cosine of x to the 3rd, and then cosine of x to the 5th. But cosine's adjacent over hypotenuse, or x over r. And then there's some simplifying we can do. We can make it -5 to the 5th times 25 minus 7x squared to the 3/2. And man, it's over 5 to the 3rd, so that's really -5 squared, so -25 over 147, and then plus 25 minus 7x squared to the 5/2. 5 to the 4th cancels with 5 to the 5th, so we get 5 times 49, which is 195 plus c. That's the answer, and that's how to do it using trig sub. You could also have done u sub from the beginning, and du then is -14x dx, so you can get one of the x's there and solve this for x squared. X squared is u plus 7 over 25. And so like you could separate out one of the x's and then put this in place of x squared. You're still gonna have a lot of algebra, but I think it's not quite as horrible as what we just did. Either way, it's not a fun problem, which is probably why it's the last one of the trig sub assignment that I gave you guys, or trig sub worksheet I gave you guys, but that is it. All right, we are 2 minutes over, so I will stick around to answer like last minute kind of informal questions, but that is it for tonight. Is the video from the 12:30, the one from earlier today, that review is posted already. This video may take a while to process. If it's processed before about 1 in the morning, then I will post it tonight. If it's not, I will post it when I get up tomorrow morning. But if it's before 1, maybe even 2 tonight, I will get it posted tonight. Otherwise, I will wait in the morning and I'll post this review session. You can start as early as 12:01 a.m. if you want to. When you start, your time for 2 hours for me or 1 hour for people who are doing half online and half written. Your instructor should give you information about that, but 2 hours for me or for Adam from when you start. And so just make sure you are ready to sit down and take the test, and good luck. And yeah, Andy is suggesting not to do 12 a.m. That's a mistake, or 1:30 for sure is a mistake. Your brain is probably fine. Go take a break for a little bit. Study some if you like working late, but study tomorrow a little bit before you take it. Relax. You guys should be good to go. Remember that review sessions tend to get questions that are the hardest ones, which is kind of what some of these were. Not all of them, but some of them were the hardest ones. So not every problem is as miserable as these. So, all right, good luck, you guys. If you have questions, stick around. If not, I will see you later. Good luck on the test.